The 3-axis machining center is one of the most common types of CNC machines used in manufacturing, allowing you to make anything from simple 2D brackets to complex free-form shaped components. It is essential that manufacturers can maximize the full potential of these machines to reduce overall production times and increase profit margins. If you're using Autodesk Fusion today and have dismissed the manufacturing extension because you feel it only benefits 5-axis programmers, then stick around. We're about to reveal some of the biggest ways that the extension can help 3-axis programmers to reduce the time needed to get your CNC machine making parts sooner, allowing you to make better quality parts and produce them with greater levels of efficiency. In this demonstration, we will review the capabilities of the manufacturing extension and their advantages for your everyday programming tasks on 3-axis machine tools. Although these demonstrations use a plastic injection mold, it's important to mention that all these functions and scenarios are applicable to various other parts and production machining too. Many parts have holes which need to be drilled. If there are only a few, then this is relatively straightforward, but a lot of components have many holes which are different in type and size, increasing the time that is needed for programming. Fusion's automatic hole recognition automates the process by detecting the holes and automatically applying customizable templates of your standard hole-making processes. Let's look at this core plate, which has many holes to be drilled. You could manually create all the toolpaths needed, but measuring each hole and selecting the correct toolpath is time-consuming and open to errors. Also, different hole types typically require more than one process to machine them, further increasing the time needed. By utilizing hole recognition, all the holes can be automatically identified and listed. Then machining templates can be applied to each. These first 8mm holes are ejector pins, which we want to drill from the opposite side, so we will flip the hole direction so that they will not be considered. The 16mm holes will be drilled, but the 29mm holes are the guide pins, which are already in the plate, so we can ignore them. The 22mm holes are correctly identified, but the 4 and 5mm holes are tapped, so we will set the correct action and verify the thread type. The 6 and 8mm holes are also listed but excluded to be machined from the backside. We want to drill them in this setup so we can select and flip the hole directions. From the Tool Libraries tab, you can select the libraries to use in the toolpath creation, and the Options tab has additional parameters that can be used if needed. By selecting OK to the form, all the toolpaths needed to complete the drilling in this setup have now been created. Much like other strategies inside Fusion, these drilling toolpaths can be modified if further changes are desired. Fusion's automatic hole recognition significantly enhances your CNC machining workflow by streamlining your hole programming for increased efficiency and consistency, as well as sharing best practices across your team. Complex geometries contain areas which are more vertical and others that are near horizontal. To machine these to a quality surface finish, it's best to address them differently. Creating the best toolpaths manually takes a considerable amount of time and skill, as you will need to accurately select the steep and shallow regions to machine. Choose the best toolpath type for each area and ensure the toolpaths overlap each other in order to remove any witness lines that would otherwise be left on the machined part. The steep and shallow toolpath in Fusion simplifies this with one toolpath which automates the programming process. This mold cavity is a great example. Its geometry has regions that are near vertical and horizontal. Additionally, there are areas which fall in between. Ideally, the steep and shallow regions should be machined using different strategies that ensures we achieve the best surface finish. We could isolate each area creating individual toolpaths, and then create secondary toolpaths to address areas missed or needing additional attention. This is inefficient both in terms of CAM programming and actual machining times. If not done correctly, surface finish quality could be lacking as well. Steep and shallow can address this entire area with one toolpath. After identifying the complete area to be machined, we can move to the Passes tab where the areas to be recognized can be set. The steep and shallow toolpath offers a number of advanced options to provide enhanced control. First, we can define a threshold angle to control whether a region is considered to be steep or shallow. Next, we can choose whether to create a single toolpath that machines both steep and shallow regions together, or have Fusion create toolpaths for the steep or shallow regions only. The overlap distance automatically overlaps the two toolpaths, which is essential, increasing the finish quality with the removal of witness marks between the two toolpaths. Each region can have its own parameters. Steep passes, which step down the z-axis, can be spiraled to limit cutting interruptions and have a step-down value defined. Fusion can also machine undercut regions when using a lollipop type cutter. Shallow passes can utilize a choice of two different types of machining, parallel or scallop, with a step-over value independent from the steep regions. Sudden changes in direction can leave tool marks with options to spiral and smooth offsets. You can reduce these sudden direction changes, leading to increased surface finishes. After calculation, we can see the area has been machined with two different machining styles in the correct regions, and a proper blend has been applied between them, all within one toolpath. Fusion's intelligent approach to machining different areas of geometry with the steep and shallow toolpath simplifies your programming process and reduces the time needed to create toolpaths for the machining of complex geometries. One of the most important aspects of any machining project is the quality of the finish, especially in the corners, where there are localized regions of stock that need to be removed safely and efficiently, while also managing the load on the cutter to avoid breakages or achieve the correct surface finish. Autodesk Fusion offers a unique toolpath called Corner, which is designed to enhance the finishing of corners in your machining projects. We have finished this cavity with a 6mm ball end mill, but there are many fillets and areas which need to be machined further with a smaller tool to reach the final geometry shape. There are multiple issues we must contend with here: identifying the areas, isolating them, and machining them in a proper way to create a quality finish. The corner toolpath can simplify this for us. In the form, we have selected a 3mm ball end mill, which we want to machine with. Next, moving to the Geometry tab, we can identify the previously used tool in the rest machining and enlarge it so that the detected area will be expanded over the previously machined surface. In the Passes tab, we can set the parameters for how the steep and shallow regions are addressed independently, as each can benefit from being machined in a different way. After calculation, we can see that all the corner areas have been detected, and toolpath has been created to machine them. Zooming into this end of the cavity, we also see that the steep regions are machined with the tool going across the fillet, and in the shallow areas the tool follows along the fillet, automatically creating a toolpath that machines all the corners in a way that avoids shock loading the cutting tool, while also achieving the optimum surface finish. By utilizing the corner toolpath for finishing in Fusion, you can achieve a smoother and more accurate finish in the corners of your parts, while saving time and reducing tool wear. Swarf machining, which is the process of using the side of an end mill to follow a geometry shape, is typically thought of as a 5-axis machining process. But many shapes, such as a vertical wall connected to an irregular floor, can be machined in 3 axes and can benefit from this process as well. The advanced Swarf toolpath in Autodesk Fusion can be limited in the axis of motion, allowing you to quickly create Swarf-style toolpaths which are able to be run on your 3-axis machine tool. This pocket is a great example. A 2D toolpath will not work as the floor is not flat and perpendicular to the wall. You could use Fusion's contour toolpath, but this will not follow the floor and will create steps in the fillet which will have to be machined again with a different toolpath to be finished properly. In the Advanced Swarf dialog, we can first limit the number of axes used to drive the toolpath to 3. Next, we can select the faces we would like to machine and the faces which make up the floor. The Tool Tracks Floor option allows the tool to trace the floor shape, removing undesired steps in the finish. From the Passes tab, parameters can be set to control the machining process. In this situation, we would like to cut down the face with multiple passes, and we would also like these passes to blend from the top to the bottom. The resulting toolpath swarf cuts the pocket wall while following the geometry of the floor, allowing for a quality finish to be machined, yet only using 3-axis motion. The flexibility of the advanced swarf toolpath in Fusion allows the creation of efficient swarf-style toolpaths suitable for 3-axis machine tools to enhance the versatility and efficiency of your machining processes. In manufacturing, parts typically have sharp edges and burrs after the machining which need to be removed from the final product. This process is commonly done manually, requiring the use of employee resources, which could be better utilized in other areas or with time-consuming CAM programming. Autodesk Fusion's deburr toolpath works seamlessly with both chamfer mills and ball end mills to automate the creation of toolpaths for part deburring during the machining process. From the dialog, we can select the edges to deburr. The automatic option will identify all sharp edges of the component, but in this situation, we would like to control the selection manually as we just want to remove the burrs from the pockets and plate. This can easily be done by just selecting each edge. From the Passes tab, we can define the machining process and the edge type, which can be a chamfer or a fillet, along with the intended size. In the case of a fillet, multiple passes will be created to machine the radius to the correct size. In this situation, we just want a small chamfer to remove the burrs that were created during machining. The final toolpath uses a ball end mill already in the machine from another process to follow the edges and break them. Fusion's deburr toolpath is a game changer, bringing increased efficiency and accuracy to the post-machining process, smoothing edges to perfection, and helping to achieve the highest quality of the final product. There are times when your software creates toolpaths that aren't quite what you had in mind. In most systems, your only option is to change some toolpath settings and try again. Autodesk Fusion is different and provides a suite of modification tools that can be used to quickly turn a good toolpath into a great one, all without having to recalculate the entire toolpath again, saving time and effort. Toolpath modifications can be incredibly useful. Let's look at just a few examples of how they can help you with your daily workflows. Engineering changes are common, and here there has been a change to the geometry at the end of the core requiring us to remachine it. The original toolpath has been updated with the new geometry, but it machines the entire core, and we just need the end section. With the trim option, you can remove or keep a selected area. Creating a polygon by graphically selecting points, we can trim the rest of the unneeded toolpath away. This specific modification is also listed in the toolpath timeline, meaning that the modification can itself be changed. If we need to adjust the defined area, for example, maybe we want to increase the distance the toolpath blends onto the original, we can simply edit it and click OK. Now, in addition to trimming the entire toolpath to the end, there are toolpath segments in the center that we do not need. The delete option can help here as it allows us to select and delete one or more toolpath segments, either using a single click or a window selection approach. Once all passes are selected, we simply click OK and they're removed, again all without having to recalculate the entire toolpath. There are times where one tool may not be enough for an entire toolpath. Here both mold cores are being machined together, but it would be better if each used a fresh tool. Using the trim option again, we can use a y-axis plane placed between the cores and choose the option to keep both. Then selecting one of the toolpaths and using the replace tool option, we can update the toolpath to use a new tool of the same type and size so that each has its own tool. Making this change manually would require duplicating the toolpath, editing the boundaries, and recalculation of each, all of which means more processing time and effort. It happens more than we would like. The machine needs to be stopped in the middle of a long toolpath, and the safest thing to do is restart at the beginning and waste valuable time cutting air. Using this mold core block again as an example, with a quick measurement on the part being machined from the parting line to where we stopped, you can remove the toolpath already completed to remove the air cutting segments and eliminate the wasted time. Another common request is to have more control on the exact location where a toolpath starts cutting. In pocket machining, for example, the entry and exit points can sometimes be positioned in an undesirable location, such as here where they fall on the mold shut-off face. It would be better if these points were moved to a different area. The Move Entry Positions option allows you to move these points to the location you desire. By defining a line across the toolpath segments, the entry positions are moved to the intersecting point. We can take this one step further. By defining the line diagonally across the segments, the position of the link moves will be staggered as well, helping to reduce the likelihood of witness marks being left on the part. Fusion's toolpath modification functionality heralds a new era in computer-aided manufacturing, offering unparalleled customization and control to create the toolpaths you need when you need them. The traditional manufacturing approach after machining is the removal of the part from the machine and inspecting it on ACMM. If manufacturers do this and find the part has errors, it is often too late to fix them, so better to find faults early to avoid making a scrapped part even worse. Even if the faulty part can be fixed, the additional time needed to remove the part off the machine, inspect it, figure out what's wrong, then set it back up on the machine a second time, adds time and cost to the process. Probing can help remove all of this waste. The wall of this pocket is a critical feature that we want to verify is correct, so let's create an operation to inspect it. By using the probe geometry option, we can create operations to inspect features like holes, bosses, walls, channels, and corners. From the form, we will select the wall face in question and choose to do planar fitting. Notice that the inspection points are automatically created. We can define the strategy used to create the points. Here we will use the edges strategy and increase the number of points to 6. The positions can be fine-tuned using the shift position slider. We will then input an approach value, define the tolerance band, and the operation is complete. The mold core geometry needs to be inspected as well, but is more complex. Here we will use the Inspect Surface option, which gives you fine control of the points to be probed. The selection process is graphical, allowing you to select where on the geometry you would like to place the inspection point and fine-tune its placement if needed. Once all of the points have been selected, we will again set an approach distance and the desired tolerance band. Once created, these operations can be exported as a in-C program. They will then be run on the machine tool, during which each inspection point result will be recorded, creating a file that then can be downloaded and imported into Fusion to review the results. Graphical representations of the results are shown, and inspection reports can be generated, then exported for your records, giving you confidence that your part meets quality standards. With capabilities extending from the inspection of intricate freeform surfaces to the detailed examination of prismatic geometry, Fusion's probe inspection can make your CNC machine's probe an indispensable part of your workflow, allowing you to achieve the high standards demanded in today's competitive manufacturing. Setting up a component on your machine tool that is complex in shape or previously machined can be a difficult and time-consuming process. Part alignment in Autodesk Fusion offers a revolutionary solution that streamlines the setup process, ensuring that operations are carried out with utmost accuracy and efficiency. There's been an engineering change, and we need to set this core plate back up for additional machining. Positioning is crucial, and the traditional approach would see a lot of time being spent manually indicating and measuring the part position, then gradually moving it until it's ready for machining to begin. A better alternative is to utilize the Machine Tools Touch Probe and use Fusion to align the in-C program to the part's location on the machine. In this example, we will set the alignment method to be 3-axis, and as we only want translation along X and Y axis, we will uncheck the Z. We next need a probing operation to determine the core's current location. Using the Inspect Surface option, we can graphically select and adjust the points on the core to be measured. Additional parameters such as the approach distance and the tolerance band can be set to finalize the operation. This probing operation is then exported as a in-C program, which will be run on the machine tool. During the probing, each inspection point measurement is recorded in a file that can be downloaded from the machine controller and loaded into Fusion to review the results. With the results imported, we can graphically see the deviation and inspection reports of the current part location. Fusion can now automatically calculate the necessary translations in X and Y and display the effects to confirm that the alignment is within predefined tolerances. With the part's location mapped, we can now export the machining in C program with an alignment applied, which will consider the inspection results and adjust the output of the in-C code to take into account the transform calculated by the alignment. Part alignment can be even more useful in production machining when using preformed shapes such as castings and forgings, or in the secondary post-processing of additive parts. The integration of Fusion's part alignment into your manufacturing is a transformative step in machining precision and operational efficiency. The automation of alignment, informed by real-time inspection data, not only saves you valuable time, but also enhances the accuracy of your machining process. The Fusion manufacturing extension significantly enhances 3-axis CNC machining by automating workflows, streamlining CAM programming, increasing machine uptime, and reducing costs. Key features include toolpath automation that automates hole recognition, the machining of complex 3D shapes, corner rest milling, and the deburring of parts. Toolpath modification allows quick adjustments to be made to toolpaths without the need for costly recalculations, saving precious programming time and enabling projects to be completed sooner. In process inspection and part alignment, use spindle-mounted probes to measure parts, identify errors, and make adjustments to the machining process. This can greatly reduce machine setup times and help you achieve the highest levels of accuracy from your CNC machinery. The combined capabilities of the manufacturing extension can help your business run more effectively today, boosting productivity, improving quality, and reducing costs. The extension can also save time as much as 30 hours on a typical project, representing substantial monetary savings for your business. Crucially, the extension can also help your business to grow tomorrow, providing the tools your team needs to win additional, higher value work, boosting both your business's reputation and profit margins. And as your business grows and invests in additional 5-axis machinery, you can have confidence that the Fusion manufacturing extension provides all the tools you'll need to drive these too. Imagine a future where your production processes are streamlined, your efficiency is maximized, and your quality standards are unsurpassed. The Fusion manufacturing extension is your ticket to this future. It's not just an investment in technology, it's an investment in your potential and the limitless possibilities of what your business can achieve. Unlock all this and more by subscribing to the Fusion manufacturing extension today.